all connected really quickly there, actually. Right, I can see that everyone is connected. I'm just going to pop out my chat so that I can see what on earth's going on there. We've got, you've all kind of been to a session now, so you kind of know the drill. We've got a screen record going on one screen that I'm sharing with you through this. There is nothing kind of being recorded with names or chat or anything like that. As we do go through, I'll have an eye on the chat to kind of respond to your questions at the same time. But I will, as we're going through, because this is being recorded, won't name anyone by name. It will just be a case of I'll answer, respond to your question as it is, but not be calling out, oh, like Mohammed's asked this. The session will be uploaded onto your playlist and available from tomorrow morning. My job immediately after this is to go and immediately go and edit before I forget what on earth I meant to cut out. Your biology ones, if you were in yesterday's attendance, your biology ones are already there, so they should be uploaded and already there, ready to wait and view. And actually, that's all the biology ones are there, so we've got nice and ahead of that one. Today we're going to be looking at structure and bonding. There is some separate science content for those of you doing combined science. Once it shifts to the separate science only, there will be nothing further for combined. So at that point you're like, actually, yeah, I'm done. No, kind of like, don't feel you have to hang around. You can pose questions as we go, but once you get to the end of the separate, or the combined science I should say, feel free to skedaddle off, like it's fine. No offence kind of taken. I'm trying to get myself sorted out. Again, you kind of know that I'm recording, there will be errors as I go, so when there's that awkward kind of pause, it'll be a case of I'm just trying to make a note of what mistake I've got so I can immediately go cut it out and make sure that, fingers crossed, that doesn't turn up in the video. But if you ever do notice in the recordings that's in there, just send me a message and at least I can then cut it out, hopefully. Right. In the session, we're going to be looking at bonding, structure and properties of matter, and there is a lot to unpick within this. Why is there next getting dragged across my page? Okay. I think I was pressing a key. We'll just restart that, I think. In today's session, we're going to be looking at bonding, structure and properties of matter, and there'll be a lot of bits of content in here that feed into a lot of the questions that you can expect to see on a chemistry paper 1. We're going to be looking at bonding throughout most of this actually, and we'll be looking at the 3 different kinds of bonding, when they occur, describing bits about their structure and then linking that into properties. But to get this started, we've got 3 different kinds of chemical bonds. We have ionic, and this is a bond that forms between metal and non-metals. And within this, we have electrons being exchanged, and the exchange goes from the metals to the non-metals. We also have covalent molecules. Can anyone actually hear me? We're going to have to start. We will... How? The microphone was miles away. Is that better? Thanks, Mohammed. What's that? Just listening. I'm going to go back. This will overrun slightly. So my apologies. That is such a disaster. Right, let's go again. Is the sound now better or does it sound the same? Okay. We're there. I figured out the microphone's on the other side. Right. In this session, we're going to be looking at bonding, structure and properties of matter. Now within this exam, there is content that you could be assessed on. This will be in green. And for those of you doing combined or foundation papers, there will be some content in here that you won't be assessed in, but this will be greyed out. And I'll flag this up as we get to it. We're going to start by looking at chemical bonds. There are 3 kinds of bonds in chemistry. The first is ionic. Now this takes place between metals and non-metals, and what happens is we have an exchange of electrons. So in this, metals are donating their electrons to non-metals, forming ions that attract. In covalent bonding, these are bonds that are formed between non-metals, and now they will share electrons. while in metallic bonding, this involves metals only, and what we'll find is that we have delocalised electrons. And we'll look at each of these in a lot more detail as we continue through. So first of all, we have ions. Now we need to be able to describe in our exam what they are and how they form, and it is a very common 3 and even sometimes 4-mark question. So ions are electrically charged particles that have got either more or less electrons than they do protons, and this happens because they've either gained or lost electrons. Metals tend to lose electrons while non-metals tend to gain them. So positive ions, for example our metal ions, are formed when they lose their electrons, while non-metals are going to form negative ions. Now the reason that these ions have got the charge is down to the fact they no longer have the same number of protons and electrons. So in this case, when we're forming a positive ion, it's the idea when they've lost an electron, they've now got more protons than electrons, and so overall have a positive charge. So if we look at this example, sodium has lost 1 electron in this. So it's 1 electron, its outermost shell's been lost to get a full outer shell. And because it's lost 1 electron, it's going to become a +1 charged ion. Now negative ions form when they gain electrons, and non-metals tend to do this. Now because they now have more electrons than they do protons, it means they have a negative charge. Now in this example, chlorine will gain 1 electron to obtain a full outermost shell, and in doing so, it will have now 1 more electron than it does protons, and so has a -1 charge. You should be prepared in your exam maybe for 2 marks to describe how ions actually form. And the way that I'd kind of recommend to structure this is always just start by saying which group it's in. So lithium, for example, is in group 1. Then identify what's going to happen to the electrons. So is it going to lose? Is it going to gain? And how many? So in this case, it's going to lose 1 electron to get a full outermost shell. And the final thing is I'd always hedge my bets and say what charge it will get. So in this case, we'll get a lithium with a +1 charge. So calcium's in group 2. It's now going to lose 2 electrons and become +2 charged. Oxygen, which will form an oxide ion, is in group 6. So it will now gain 2 electrons and become -2 charge. So if it loses, it becomes positive. If it gains, it becomes negative. Chloride ions is down to the fact that chlorine's in group 7. It will gain 1 electron and so has a -1 charge. Be prepared in your exam to know what the different charges of ions are, and my advice here is the first thing you should do in your exam is actually write your charges above your groups, because it can help just you visualize your electrolysis questions if you're asked about how ions form, or even if you have to write ionic equations and write a formula down. So it does come in handy. So what I'd always recommend, the first thing in your exam is write +1 above group 1, +2, and then across in group 3, +3. So this is lost 1 electron, lost 2 electrons, lost 3 electrons. Leave a gap, and then it's -3, -2, -1. So I'd always say, as soon as you're told you can begin in your exam, just start by writing that down. It means also you then know exactly the first thing that you're going to do in your exam paper, and almost then just gets you off to that start of, there's no kind of mystery about what the first thing in your exam is. You're like, right, I'm just going to write these numbers above. So with this, these charges are all down to what's happened to these atoms to give them a full outer shell and how they've become ions. So group 1 all lose 1 electron, group 2 all lose 2, while group 3 will all lose 3 electrons. We then kind of miss a gap, and over in group 7 we now gain 1 electron, while group 6 we gain 2, and in group 5 we gain 3. So that the number that it's gaining or losing determines the number of the charge, but if it's losing, it becomes positive. If it's gaining, it's going to become negative. You might also be asked to draw a diagram of this. So for example, here we've got our group 1, This is our lithium metal, so it's in group 1 of the periodic table because it's got 1 electron in its outermost shell. And to become stable, it's going to lose that electron. So here we've got our lithium ion. Notice it's been redrawn, but it's now missing its outermost electron. When we draw these, we need to make sure with the ions that we put them in a square bracket to indicate that they're ions, and we need to show the charge on the right-hand corner. Here we've got our group 7. So now this is our non-metal fluorine. It's in group 7 of the periodic table because it's 7 electrons in its outermost shell. With our ion, it's now gained an electron, and notice how I've represented this with a cross rather than a circle. So we're showing this has come from somewhere else. Now this is our fluoride ion, and it's now gained 1 electron, and it has a -1 charge indicated by the negative in this corner. But to show it's an ion, we need to draw this in a square bracket. And remember, we still include that charge in the top right-hand corner. So as a general overview, group 1 loses 1 electron and gets a +1 charge. Group 2 loses 2, and group 3 loses 3. So notice those are our charges that we'd write above our periodic table columns. By the time we get to group 5 though, they now gain 3 electrons to get their full shell, so they have a -3 charge. Group 6 will gain 2, and group 7 will gain 1. So, as a further stretch to this is what your periodic table would look like in your exam. You've made those annotations above. But you might be asked to actually find the formula of an ionic compound, and this tends to be a trickier skill. Be really systematic about how you do this. The idea around ionic compounds is that positive and negative charges attract each other until actually there's no charge overall. So we're looking at a neutral charged molecule. So we need the positive charges and negatives to cancel each other out. So here we've got our periodic table and also some other common ions and their charges. And it's well worth kind of having these on flashcards and learning beforehand. Ammonium comes up a bit less, but the rest come up. Sulfate, for example, if they've been mean, can come up. Now I use the swap, drop and cancel method. Now the way we approach this is, well, first of all, let's say we're looking at aluminium oxide, is you will identify the ions that we've got. So my aluminium is kind of hidden in here, but it's in group 3, so it's a 3+ ion, and my oxygen's over here, so it's a 2- ion. So my planning, I'd write my chemical, I'd write my ions underneath. And then I would swap, drop and cancel. So we swap the charges across. Notice how I've got rid of my pluses and minuses. I then drop them down, and we then cancel this out. So we're finding a common denominator. Now this one's already, we don't need to cancel this any further. And so at this point, we just move our symbols closer to each other, and that will give us the formula for aluminium oxide. If we try aluminium nitrate, for example, again, we use the same method. So we'll identify a chemical and we'll identify the ions that we're going to use. And then we go back to our swap, drop and cancel. So there should be, so our nitrate was a -1. So actually aluminium is just now 1. While the aluminium had a +3 charge, which has gone across here. Now we'll drop these. And notice, when I drop that 3, I end up with 2 3s very close together. And so what we need to do is place a bracket around that to say, right, I don't have 33 oxygens, because that's what that kind of suggesting, but actually I've got 3 lots of what's inside that bracket. And then at this point, we cancel and find the common denominator. And again, that's as kind of cancelled down as we can get. So we'll place those 2 symbols closer to each other. Now, a very common 4-mark question is to explain how ionic compounds form. There's no way of predicting the exam which compound it might be. It might be sodium chloride, it might be magnesium oxide, but you will always have elements on your periodic table, one from group 1, 2, 3, and one normally from group 6 or 7. We can't predict which compound it will be, but the way you answer this will always be the same. Talk through what's happened to your metal ion. So for sodium, for example, it was in group 1. It has lost 1 electron and become +1 charged. Chlorine was in group 7. So therefore, it's gained 1 electron and become -1 charged. So we give a really detailed answer of what's happened to our electrons in both the metal and the non-metal. So how many have been lost by the metal, how many have been gained by the non-metal, and say their charges. Now the final step here is to identify that these opposite charges are going to electrostatically attract to form an ionic bond. The only thing I'd say to be really careful about is that sometimes, let's say there's some magnesium that's given away 2 electrons, well actually 1 magnesium will bind to 2 chloride ions in this example because it would have a 2+ charge. So it's worth being aware of, but always just say what's happened to your metal, it's lost how many, what's happened to your non-metal, it's gained how many, and then say they electrostatically attract each other. So the sodium atom has lost 1 electron, it's become a +1 charge. The chlorine atom has gained 1 and become a -1 charged chloride ion, and the electrostatic force of attraction between the Na+ and the Cl- is forming that ionic bond. So here, for example, we've got some further ones, so sodium and fluorine. So notice we're going through that same writing frame. Sodium's going to lose 1 electron to become +1 charged. Fluorine is gaining 1 electron, and there's an electrostatic force of attraction. And 1 sodium bonds to 1 fluoride, so the charges cancel each other out. Over this one, similar story with magnesium, but now it's losing 2 electrons because it's in group 2, and oxygen's gaining because it's in group 6, sorry. And then over here, a bit different. So calcium's losing 2 electrons, so it becomes +2 charged. Chlorine is gaining 1 electron, so it becomes -1 charged. So those numbers no longer match. We can still talk about the electrostatic force of attraction, causing those to bond together, but now 1 calcium ion is going to bond to 2 of those chloride ions. So it's a little bit of a stretch further. If you were modelling this, what you would do is you draw your electron configuration of your atoms going in, and then you would show what's coming out. Here you would redraw with your full outermost shells, remembering to put your ions in their brackets. So we'll draw the atoms, and the ions must have those brackets coming out. With the actual structure of an ionic compound, there are some key phrases that we need to use. So you might be asked to describe the structure of an ionic compound, but be aware it can sometimes get hidden in a 6-mark question where you have to describe the structure and properties of an ionic compound. But the key phrases that you need to use is that they are a giant lattice, and this is a reference to its regular structure. Now the positive ions and negative ions are attracted to each other in this regularly repeating pattern, and we've got very strong electrostatic forces of attraction between them, forming this ionic bond. And that's what's holding all those ions in position. Now our next kind of bonding is a covalent bond, and this is one between non-metal atoms where they are sharing electrons to achieve a full outermost shell. So these atoms are very strongly held together because these electrons that are negative are both attracted to the positive nucleus of this hydrogen atom, but also are attracted to the positive nucleus of this oxygen, and so they're held in the middle in this really, really strong bond. Now this has been done to achieve this full outermost shell. Within this, and it happens with the halogens quite a lot of our simple molecules can be diatomic, and this means that we've got 2 atoms covalently bonded together, so they're paired up, and all the halogens will always be diatomic, so F2, Cl2, I2. And these are some common diatomic molecules that you might be asked to draw in your exam, and you would get given a couple of marks for them. We have simple molecules with covalent bonds, but we also have some larger molecules. So polymers have covalent bonds between their atoms, and we've got giant structures like diamond and silicon dioxide that have covalent bonds too. Now you could be asked to draw a dot and cross diagram for some diatomic molecules, but also even water and ammonia. So when we do this, be really procedural around how you approach it. You want to first of all figure out the number of electrons the atom has in its outermost shell. So for example, if we were looking at chlorine, it's got 7 electrons in its outermost shell. We'll write the symbol for the first atom, and we'll then figure out how many more electrons it needs to get a full shell. So in this case, chlorine needs 1 more. We'll then draw an empty shell around the atom and a second one overlapping. Now, if we know that they need 1 more electron to get a full outermost shell, that means that they must be sharing 1 electron each between them. So 1 pair of electrons has to be shared, and we draw this in the overlapping region. What we then do is go around and fill in the remaining electrons. So both of these will then have 6 more unaccounted for to complete the outermost shell. So here are some really common ones you might be asked to do. So we've got hydrogen, oxygen, nitrogen, fluorine, chlorine and hydrogen fluoride, or we could have hydrogen chloride. So just be aware that should say hydrogen chloride, so HCl. If that were hydrogen fluoride, it would be the same restriction arrangement, you just have an F there instead. But these are all the ones you might be asked to do within your exam. It's best to be able to do the method of it, so you're confident in how you draw these, whichever one they then ask, but you could also put these on flashcards and learn before you go in. And if these do come up, it'd be a mark, well, 2 marks normally, unless it was hydrogen. As our final bond, we've got metallic bonds. Now these are made up of metals that will lose electrons to get their full outermost shell. So the electrons in the outermost shell of that metal are delocalised and form a sea of electrons around the positive metal ions. The electrons are attracted to the positive ions, and the positive ions are attracted to the electrons, and this is what forms the really strong bond. You might be asked to describe the structure of a metal, and here a really good phrase to use is giant lattice. So we've got this really regular pattern, and there's lots of these atoms, or ions I should say, involved. So we've got these positive ions in this giant lattice structure, and it's a reference to this regular kind of structure that we see. Now they are surrounded by a sea of delocalised electrons. So you can either refer to them as a sea of electrons. I'd say the better answer is to say delocalised electrons. We want the idea that we've got positive ions surrounded by delocalised electrons. And it's the sharing that's forming that really strong bond. We're going to come back to different types of bonding and the properties of the material shortly, but we'll also just need to touch on the particle model around solids, liquids and gases. And you should be prepared in your exam to maybe model the arrangement of these particles in solids, liquids and for gases. Now when we draw solids, we generally want to draw these in a really regular arrangement and layers and make sure that all our atoms are kind of touching each other. There should be no gaps in between. Now with liquid, this one actually has got some room for improvement. With a liquid, you would draw your atoms, again, more jumbled up, but they should all be touching. And what we should see is there should be very few gaps. Now what we should kind of see is that most particles are touching another one. So actually there's a few too many gaps in this diagram. That could be a better kind of depiction. So you want to have no gaps between these. The way the examiner will kind of assess, because it's hard, you want them jumbled, is you need to make sure that each of your particles is touching another one. That'd be kind of a good way of making sure, sanity check, they're close enough. Now with a gas, they now need to be random, far apart, with very large gaps in between. And you do want them to be random, so avoid like faces of dice that you might see. Now for higher content only, you might be asked to kind of talk about limitations of particle models. And in this case, the particles are shown as spheres. Molecules aren't spheres with multiple atoms attached to each other. They can sometimes be quite linear. And they're also shown as solids. And we know that atoms are not solid objects. They also don't really show the forces that there are between the particles. It's only 2D, and it's actually quite hard to depict the movement. So these solid particles are vibrating backwards and forwards, while these are moving freely, and these are moving freely and a lot faster. So again, it's not referencing the speed those particles are moving. So there are some limitations and restrictions on this model. Now there are two key phrases to be aware of. We've got melting point and we've got boiling point. The melting point is the temperature at which solids turn into liquids, but also liquids turn into solids. So the melting point of water is 0. That is the point at which it will both melt and it will freeze. The boiling point of water should be 100. So that will be the point at which it will both evaporate and turn into a gas, but also the temperature at which it will condense and turn back into a liquid. So at each point, we've got two state changes that can happen. So one thing we'll talk about this a bit more when we get to simple molecules is that if we want to change the state, what we need to do is overcome the forces or bonding that there is between the molecules. And typically the stronger these forces are, the higher the melting point is going to be. A common question that, for honesty, I actually struggle with sometimes is you might be given a data table and asked what state of matter something is. And because the negative numbers, it can sometimes look a bit confusing. You need to ask yourself two questions when you're predicting the state it's in. So if we're asked for the state at room temperature, you need to ask yourself the question, has it melted and has it boiled? So for fluorine, it's both melted and boiled, it will be a gas. Chlorine has both melted and boiled, it will be a gas also. Bromine has melted, but it hasn't boiled. And so that means that actually bromine is a liquid. Now water at room temperature has melted, but again it's not boiled, and so that will be a liquid too. Mercury has melted, but not boiled, so it's also a liquid, while sodium has neither melted nor boiled, and so it will be a solid. And those are the two questions to ask yourself as you're progressing through. Different state symbols, we've got solid, liquid and gas, which are S, L and G. Aqueous solution or dissolved, you would see AQ. And be prepared to use those in symbol equations. So we're going to go back around now and start to look at the properties of these different structures. So ionic compounds tend to have really high melting and boiling points. And whenever that's the case, it's because the bonds are incredibly strong. Now specifically for this, it's the electrostatic forces of attraction, those ionic bonds, that are really strong between these ions. And also, there's a lot of these bonds. It's a giant structure. What that's going to mean as a consequence is lots of energy is going to be needed to overcome these bonds. And so as a consequence, the boiling point is going to be really, really high. But be prepared to discuss it's not just that the bonds are strong, but that there is lots of those bonds too. Now, different ionic compounds do have different melting and boiling points, and there have been some sneaky questions behind this. So it's all down to how strong those bonds actually are. So ions have got larger charges. So let's say aluminium with a +3 charge will have a much stronger electrostatic force of attraction than lithium with a +1 charge. So it does mean that not all ionic bonds are equally as strong as each other. So the bond between chloride and lithium will be weaker than it will be for aluminium because that's got a much bigger charge on it. So if you're ever asked to explain why ionic compounds have got high melting and boiling points, it's typically 2 marks. You want to say that they're giant structures with lots of strong bonds between ions, and therefore lots of energy is needed to overcome this. Now, as another property, ionic compounds can't conduct when solid, but can when molten or dissolved. Now, this can be assessed when you're asked around ionic compounds. It can also come up around electrolysis. Now, with this, the idea is that current or electricity is the flow of charged particles, and ions are charged particles. When these are solid, the particles are unable to move freely. They're vibrating, but they can't move freely. And as a consequence, they can't conduct. However, if you melt them, so you've changed the state to a liquid, or dissolved them and added them to water, the ions can now move freely, and that means that they can conduct electricity. The common mistake that people make is they start talking about moving electrons. With ionic compounds, it is the ions that are moving, and that's what you need to reference. So with this bit then, you might be asked, why can they conduct when molten or dissolved? Ions can move freely, but they can't conduct when solid because the ions can't move freely at that point. Moving back on then to covalent structures, we're going to start by looking at simple molecules. Now, simple molecules tend to have very low melting and boiling points, and we need to be very precise to the examiner about why. So when we look at simple molecules, these have got attractive forces between the molecules known as intermolecular forces. They've been represented with these like singular lines between these molecules. Now, the smaller the molecule, the weaker this force of attraction is. So when these molecules get very, very small, this intermolecular force gets weaker. And these exist between all kind of molecules. But it's these that determine the melting and boiling points of simple molecules like the halogens or even water. So simple molecules have low melting and boiling points because the molecules are small. And what that means is that the intermolecular forces between the molecules are really, really weak, and not a lot of energy is needed to overcome these. It's important to notice that when we're melting or boiling water, we are not breaking the covalent bond. They are left untouched. That bond is really strong. But when we change state of simple molecules, is that we're overcoming these intermolecular forces that are really weak. Because they're weak, not a lot of energy is needed to overcome them, and as a result, they've got low melting and boiling points. Now with polymers, they are now a much, much larger structure. They are large, and what this means is they've got very strong bonds between the atoms themselves. This is a large molecule, and so it's got very large intermolecular forces. And so what that does mean is it's got a much higher melting and boiling point because a lot more energy is needed to overcome this. And as a consequence, polymers are solids at room temperature. Now we're going to look at giant covalent structures. And we've got quite a few. They all typically, or they all do, have very high melting and boiling points because they've got very strong bonds. And these bonds would need to be overcome to get them to change state. Now this includes diamond, graphite, and silicon dioxide, which is represented by the equation SiO2. Now we'll come back to the properties of those giant covalent structures in a moment, but if we look at the typical properties of a metal, these are soft, they are good conductors of electricity, they're very easily bent and shaped, they're also good conductors of thermal energy, but they've got incredibly high melting and boiling points. Now for why? In a metal, if we think about its structure, we've got that lattice, those ions in the structure. Now these ions are arranged in layers, and the ions themselves are not bonded to each other. So what this does mean is that with very little force, those layers of ions can slide over each other, meaning that this is very soft, or relatively soft. They're really good conductors of electricity though, because they've got delocalised electrons. And for that second mark, we need to describe that they can move through the structure. Now they're easily bent and shaped for exactly the same reason that they're relatively soft. It's the idea the ions are arranged in layers. Those ions are not bonded to each other. Yes, they're bonded and we've got metallic bonds between the ions and the electrons, but the ions themselves aren't bonded to each other. They can slide over each other with little force. They're good conductors of thermal energy for exactly the same reason they're good conductors of electricity. The metals have delocalised electrons, and that can transfer heat and thermal energy through the structure. But they've got high melting and boiling points because we've got a giant structure with lots of bonds, and those metallic bonds are incredibly strong. And that's going to mean a lot of energy is needed to overcome these. Now linked to metals, we've got this idea of alloys, and these are now, as a definition, a mixture of two or more elements, or at least one of those needs to be a metal. Now alloys are much harder than a pure metal, and it's a very common exam question to be asked why. Now, the key ideas you need to express here is the idea that we've introduced now atoms or other ions of different sizes. And what this does is it distorts the layers. Because the layers are no longer able to slide over each other, this makes this a much, much harder material. So metals are really good conductors because of these free electrons are able to carry charge. So these free delocalized electrons can move through the structure, taking charge, but they can also transfer thermal energy as they go. So our giant covalent structures, and there are a few. Diamond is our first, and be prepared to talk about its structure and bonding. So for bonding, it is made up of, it's covalently bonded together. But this is made up of carbon atoms that are covalently bonded to 4 others. And it forms this really rigid and giant lattice. So its structure is a giant lattice, and its bonding is carbon atoms, each covalently bonded to 4 others. Now, as far as the properties go, diamond is incredibly hard because this is a giant structure, which means it's got lots of bonds, and those bonds are incredibly strong. It has a high melting point because, again, it has got a giant structure, so lots of bonds, and those bonds are really strong. It's going to take a lot of energy to overcome that. Now, it can't conduct electricity because there's no free electrons within this structure, and so there's no charge that's able to move through. When we get to graphite, again, you might be asked to describe its structure and bonding. Now, graphite is also a giant lattice, and in this case, it is still made up of carbon atoms, but now each carbon atom is covalently bonded to 3 others. Now, what this means is we get these almost like hexagon layers, and these are not, as these layers go, are not covalently bonded to each other. These dashed lines are representing intermolecular forces of attraction. So these layers are not bonded together by any covalent bond. So it does mean that between these layers, we've got a very weak intermolecular force. So as far as the properties go, graphite is actually relatively soft. And it's because of the fact that we've got these layers with weak intermolecular forces between them, they can slide over each other with very relative little force. They've got a very, very high melting point because, like diamond, they're a giant structure of lots of bonds, and those bonds are incredibly strong. So lots of energy is needed to overcome this. This one can conduct electricity because it's got, for 1 mark, delocalized electrons, and for the 2nd mark, they are able to move through the structure. Now with this, we start to go into our graphene and our fullerenes. So when we look at our fullerenes, these are now a molecule in which we've got a hollow shape and we've got carbon atoms making this up. Now our carbon atoms are covalently bonded to 3 others. So it's like one single layer of graphite, but it's kind of rolled into a ball. So we've got these carbon atoms covalently bonded to 3 others. Now the first as a 1 mark fat recall to be discovered was Buckminster fullerene, which has the formula C60, and this is a rounded shape. Now the properties of the fullerenes are they are slippery, and it's down to the fact they've got this rounded shape. They also have a low melting point. The fullerene, Buckminster fullerene, has the formula C60. Now although that sounds quite big, it is still a simple molecule. So this has got simple molecules have weak intermolecular forces between them. So we can start to recycle our answer about why water's got a low melting and boiling point. When we boil this or melt it, we are not breaking these covalent bonds. Instead, we're breaking the intermolecular forces between them. So this is a large simple molecule, but it is still a simple molecule. But it can conduct electricity because it's got delocalized electrons which can move freely through that structure, carrying the charge as they go. Now we also have our graphene, which is a single sheet layer of graphite. So it's a single layer of carbon atoms covalently bonded to 3 others. And this can also be into a rounded tube known as a carbon nanotube. And these are incredibly strong. And it does mean that they have a variety of different uses that make them useful in electronics in particular. So graphene, fullerenes, can conduct electricity because they've got delocalised electrons which can move freely through them. And they've got incredibly high tensile strength because of the fact that the atoms are covalently bonded to 3 others. This is incredibly strong. The only reason why graphite was slippery was because of the fact that it had layers that could slide over each other. These nanotubes and the graphene sheets don't have these layers, and so they're back to being incredibly strong because we've got a giant structure with lots of strong bonds in them. Moving on to the separate science only content. The final section of this is being aware of nanoscience. Now this refers to structures that are between 1 to 100 nanometers in size. And so what we're seeing here is this may contain a few hundred atoms. They are very, very small. And we've got this coarse and fine particles. Nanoparticles are smaller than this. Now sea spray is an example of a nanoparticle. Fine particles are bigger. So nanoparticles between 1 to 100 nanometers, while fine particles are between 100 to 2,500 nanometers. So actually that's 2.5 micrometers now. So their diameter tends to be between 1 times 10 to the power minus 7 and 2.5 times 10 to the power 6. Now they're otherwise known as PM 2.5. So notice it's about the diameter that we've got in there. And smoke from a candle is an example of a fine particle. We then have coarse particles. Now they are from 2.5 times 10 to the power 6, they're kind of where the fine particles leave, and go up to 1 times 10 to the power 5. And they're otherwise known as PM10. And dust is an example of a coarse particle. Be prepared, there might be calculation questions in your exam. And so being asked to calculate surface area or volume or surface area to volume ratio could be a possibility. So for surface area, we measure our length times width, and if this is a cube, we're going to times it by 6. While for volume, we're going to do length, width and depth and multiply those together. So if we have a look, we've got 2 cubes. One has got a length of 10 centimetres and the other 1 centimetre, so it's 10 times smaller. The surface area of this one will be 600 centimetres squared. The volume will be 1,000 centimetres cubed. And actually, if we then do its surface area to volume ratio, we're going to end up eventually at 0.6. Now, if we look at our centimetre one, this now has a surface area of 6 centimetres, a very small volume of 1 centimetre cubed, and it's got a surface area to volume ratio of 6. So it's actually got a much bigger surface area to volume ratio. So as the surface area is decreased by a factor of 10, so I've made that 10 times smaller, the surface area to volume ratio increases by a factor of 10 and gets 10 times bigger. Now there's links to nanoparticles because these are particles that are incredibly small. So these have a much, much higher surface area to volume ratio than bulk materials that are much bigger might have. Now what that does mean is their properties can vary down to that huge surface area to volume ratio. It can affect both their physical and their chemical properties. We have different uses for nanoparticles. This can include medicine, electronics, we use them in deodorants, as well as cosmetics and sunscreen. They're also really useful as catalysts as well. Now there are pros and cons of using nanoparticles. Now they're really effective as catalysts, and they can catalyze different reactions and can actually make different products. And they tend to be cheaper because you don't need as much. However, there are concerns that they might be breathed in and could potentially cause harm. They might actually, if we're using inside the body, maybe catalyze reactions in the body that are harmful to us. And there's a concern that actually toxic substances could bind to these nanoparticles, causing potential harm.